So, good morning, afternoon, or evening, everyone. My name is Marie-Constance Corsi, and I'm truly glad to chair this first edition of the Trainee Spotlight event, organized by the Postdocs and Students Committee of the BSI Society. So, opportunities for trainees to get feedback from their preliminary work from experienced researchers are scarce, and more specifically during this pandemic. So, this is particularly true for students from small research groups, sometimes isolated within their own institution. So the aim of this event is to provide constructive and well-informed feedback to the trainees. We strongly believe that it will improve their chances for publication in the end. So here, each presentation will include a 10-minute talk with 5 minutes for Q&A. The last 15 minutes of the session will be dedicated to a panel discussion. Even though it will be the occasion to enable further discussion regarding the presentations, it will be also the occasion to answer specific questions asked by the speakers themselves. It can be associated with the methods, perhaps to provide tips, or also to improve their own research skills. So here you can also ask questions either via the Q&A box, and I will lay them to the speakers, or you can directly raising your hand, your virtual hand, of course, if you prefer to interact with the speakers. So let's start with the first speaker, Derek Chung, who is a PhD student from the University of Texas. His research focuses on the development of the multi-scale dynamical model to integrate multimodal brain signals and to illuminate the mechanistic understanding of brain computation. He will give a presentation entitled Multi-Scale Dynamical Modeling for Spike and LFP activity, using a neural graph network. Derek, the floor is yours.
Okay, thanks for a great introduction. I will. The slide's good. Okay. So hi everyone. My name is Derek. I'm the third-year PhD student from Santa Cruz Lab at the University of Texas at Austin. It's my honor to be here to present my ongoing work entitled Multi-Scale Dynamical Modeling for Spike and LFP Activity using a neural bound graph network. So what is my motivation? So the brain is a hierarchical system of multiple levels of organization. At the microscale level, genetic and molecular processes shape the morphology of the neurons. And these neurons are the building blocks of the nervous system. Then it forms the anatomical infrastructure for neural communication. So to get deeper understanding, it is important to study the multi-scale organization. And also, in recent years, more and more simultaneous multi-scale recordings are available. For example, for non-invasive measurements, we have EEG and fMRI. For invasive measurements, we have spikes and LFP. However, currently we do not have an integrative framework to analyze those multi-scale data. So here, in my previous work, I proposed a method called MBGNet to characterize signal translations between different scales in brain networks. So MBGNet stands for Neural Bound Graph Network. It's a recurrent neural network that uses prior knowledge about the system during model training. And that prior knowledge is based on the bound graph. So bound graph is a modeling tool widely used in the physical system. And a key feature of bound graph is multi-domain modeling. For example, the DC motor converts the electrical energy into mechanical energy to rotate the plate. And bound graph can model this physical system easily. And you can imagine that multi-scale is kind of equivalent to multi-domain, where different scales, different activities in different scales represents different energy domains. So the workflow of the MBGNet is, first, I will construct an effective electrical circuit between different recordings. And here, LFP and screwy cock are the two recordings. For someone who may not be familiar with, screwy cock is similar to EEG, but the electrodes are implanted in the skull. so you can have a better signal quality. And once I have this circuit, I will obtain the band graph here, and then it will generate the system dynamics equations. And finally, the MBGNet will be generated from the system dynamics equations. So here, in these slides, I will show that the premier results validate the MBGNet for multi-scale modeling. So what I have here are two models, forward and inverse. Forward model predicts screwy cog from LFP, while the inverse model predicts LFP from screwy cog. And we can get a pretty low root mean square error, and the ground truth and the predictions are highly correlated for most of the channels. And we also look at the results in frequency domain, and we show that the predictions are in sync with the ground truth. And here I would like to emphasize two main features of the MBGNet. The first one is that it can reveal cross-scale causal interactions among brain regions, and also the performance is stable across multiple weeks. So the figure on the left shows that the cross-scale effectivity connectivity for different movement directions in the center-out joystick task that exhibited patterns of visual feedback and voluntary movement. In addition, we also observed several shared causal interactions over all the target directions, which aligns well with the abstraction of the hierarchical anatomy of the mammalian nervous system. And the figure on the right summarizes the proposed MBGNet can maintain the performance without retraining the model for multiple weeks. And there are more details about the model development and the results, which is not shown here. I put it in my bioarchive. If you are interested in, feel free to check it out. And so what are the missing features for this first version of MBGNet? The first is the performance. While it is good for most of the channels, but some of them are poor, and we want to improve it. Second is generalizability. Instead of modeling the relationships by ourselves, we want to utilize the formal biophysical model. So how can we improve for the next generation of MBGNet? So first, for a recurrent neural network, initial state value is important. So we add an initial state estimator in order to estimate the suitable initial state values for our MBGNet. Second, simple recurrent neural network may encounter vanish gradient issue. To address that, getting recurrent unit GRU-based recurrent structure is adapted in the MBGNet. And last, as mentioned earlier, we rather choose neurobiological models. For example, when we work with the local field potential LFP, we can use Jason-Reed model, which describes the local cortical circuit by second-order differential equations. And when we work with the spikes, we can use integrated fire model or leaky integrated fire model. So here, we name our second generation of MBGNet as MS-MBGNet, which stands for multi-scale neural band graph network. And we apply MS-MBGNet on the dataset of spike and LFP, because these are the most common invasive neural recordings. And from the middle plot, we demonstrate that MS-MBGNet accurately captures LFP activity. It also performs pretty well on the spiking activity, which I didn't show the result here. And after that, we are interested in what can MS-MBGNet provide. Actually, since this is a dynamical models, we can extract the effective connectivity from the model for both within scale and cross-scale interactions. And further exploration on the effective connectivity results will lead to more comprehensive insights of brain computation during the cognitive tasks. So the take-home message here is that, so first, we proposed an integrative approach to analyzing multi-scale brain activity, which is termed MBGNet. It can provide a more comprehensive insight on brain computations by characterizing not only the within-scale interactions, but also the cross-scale interactions. And MBGNet holds great potential to improving the applicability of real-time brain-machine interface because the cross-scale interactions actually serve as supplementary information that allows us to improve the performance. And also, the MBGNet can further provide an insight into how disease-related alterations at one scale may underlie alterations observed at other scales in mental disorders. And last, I would like to emphasize here is that although the current demonstration of the MBGNet is based on spike and LP, but this modeling can also be applied in any combination of multi-scale neural recordings. So as I mentioned, talked about in the very beginning, MBGNet is also being able to apply it on the data set of EEG and fMRI. At the end, I would like to thank my supervisor, Dr. Samantha Santa Cruz, who supports me on my research very much. And I would like to thank all my lab members, especially Kylie. Kylie is an undergraduate student who contributes this project a lot. And also, I would like to thank the collaborators, Dr. Jose Comina from UC Berkeley, and Dr. Timmy and Nina Chen from UT Austin. Thank you, and I would like to take any questions.
Thank you very much, Derek. Oops, sorry, you're in time. So, do we have any questions from the audience? Feel free to use the Q&A box or to raise your virtual hand. Just in the meantime, I will have one question actually. Do you have any limitation regarding the number of modalities you want to use? I mean, from the spatial point of view, but also from the temporal point of view. Or I mean, is it a model that can be applied to any modality?
Well, that is a good question. My intuition is that I would like to apply as much as possible for this type of modeling, and because these models can be just like a plugin if you include another modalities. If you have a clear biophysical models that can be integrated in the whole data set, then it's good. But for current demonstration, we only have been able to show the results for 2 modalities. In the future, it will be very interesting to see how it works for 3 or more modalities.
Very nice. We have one question from Samantha. How do you envision this model being used in real-time BCI, like direct application of your work?
Yeah, so it has multiple ways. So the first thing is that in the original BCIs, for example, we only have a single modalities, and even like there's a current publication that can use different modalities, but actually they only analyze those data separately. And our model, the MBGNet, can provide another deeper information that how the interactions between different scales, and these scales can provide an important information to improve the BCI performance. And another cool thing is that because for now, when we apply to the spike and LRP, spike is somewhat a little bit difficult to be implemented in the BCI because the spike is not as stable across days. So if we have the LRP, then we can use this model to assist the prediction of the spikes and use that to include our analysis. they can also improve the performance of BCI.
Thank you. Very interesting. So, since we don't have any other further question, but don't worry, if we have any, we can discuss about this question afterwards. We can directly switch to the next presentation.
Okay.
Thank you very much, Derek. So let's move to the second speaker, Claire Dussart, who is a PhD student from Paris-Brennan Institute. Her research focuses on the specificity and selectivity of neurofeedback. She works on the impact of task feedback transparency and operant learning on training to develop protocols for patients with Parkinson's disease. She will give a presentation entitled Influence of Feedback Transparency on Performance in Beta-Based Motor Imagery Neurofeedback. Okay, the virtual floor is yours.
Thank you for the introduction. Hi everyone, my name is Claire Dussart and I'm a first-year PhD student here at the Paris-Brennan Institute. So this study I'm presenting today is about the influence of transparency on performance in a motor imagery BCI. So just to introduce a bit about the topic, this is the kind of BCI we used. The objective for the user was to reduce their activity in the beta band, so in EEG, between 8 and 30 Hertz. And to do this, they perform motor imagery, meaning they imagine hand movements in this case. So learning to modulate your neural activity is a quite complex task. It's going to require learning from the participant. And the key element of this learning is really the notion of feedback. So this is the feedback that is used in most BCI paradigms. The blue bar represents how well your motor imagery is recognized by the system. You can see this is a quite abstract feedback. It is given continuously and it is unimodal, meaning only a visual feedback. However, a recent review from Alinrock and colleagues showed that to be useful to a user, the feedback should aim at being more transparent, timely, and multimodal. For this study, we focused on the transparency effect. So a transparent feedback should be strongly related to the motor imagery task. For example, if you have a feedback that shows hand movements, it's closer to the motor imagery task than the classical blue bar feedback. What we hypothesized is that if we had a more transparent feedback, it could improve BCI performance by reinforcing the sense of agency of the participant. So what is agency? It is the experience you have of yourself as the author of your actions. It's based on the coherency you perceive between what you expect from your action and what you actually observe. For example, if you blow on a leaf, you expect it to fly away. If it actually does, it's going to reinforce your sense of internal causal attribution. This sense of agency can be extended to BCIs. Since in a motor imagery BCI, the task is imagining a movement. When you're imagining a movement, you should expect to see it on the screen. So this is why the transparency of the feedback could improve the sense of agency. For this study, we wondered whether feedback transparency could influence the performance of a BCI. We hypothesized that having a more transparent feedback could improve both the performance and the sense of agency of the participant. And we further hypothesized that agency could mediate the relation between transparency and BCI performance. So to test this, we designed 3 different feedback conditions with an assumed increasing transparency level. So the lowest transparency feedback was a virtual pendulum. Then we designed a virtual hand that reproduced the movements imagined by the participants. And finally, we designed the third conditions where we added motor illusion vibrations to the hand of the participant. So this made him feel like he was really performing the movements he was imagining. All the participants tested the 3 different feedback conditions in a randomized order throughout 1 neurofeedback session. And the trial design was constructed as follows. So it lasted about 24 seconds of motor imagery. In the first 2 conditions, the participants were receiving continuous visual feedback, either with the hand or the pendulum. And in the third condition, they could receive motor illusion vibrations at certain moments of the trial. There were 10 trials per feedback condition. We could include 25 participants, 12 of them were women, with a median age of about 27 years old. For the results, we report the results from repeated measures ANOVAs, as well as Pearson and Spearman correlations. What we use to quantify the BCI performance is the logarithm of the desynchronization in the beta band that was computed over the C3 electrode which is over the left motor cortex since the movements were imagined on the right hand. We divided those values by an individual threshold in order to compute an individual desynchronization for the participants. So this is our first result. Did transparency impact the performance? You can see we reported the performance here on the left. If the value is negative, that means there was a desynchronization, so this is a good thing. And if it's positive, that means there was a synchronization. So you can see that for the transparent feedback, which was the hand, there was a better BCI performance than with the pendulum. However, in the third condition with the vibrations, the BCI performance wasn't improved by adding the motor illusion vibrations. What about the sense of agency? It was reported by the participants throughout this question. Did you feel like you were controlling the movements of the hand or the pendulum? You can see there was an effect of transparency on the sense of agency, namely that with the hand, the agency was stronger than with the pendulum. However, the sense of agency seems to have decreased with the visual tactile condition. We also report the results from user satisfaction variables, such as the feeling of success of the participants that was not different between the different feedback conditions. And finally, we quantified a correlation between the BCI performance and the sense of agency of the participants. So the stronger was your performance, the stronger your sense of agency. And this correlation held for all the different feedback conditions. As a control, we wanted to test if the stimulus induced in the feedbacks was enough to induce a desynchronization of the EEG activity. So what we did was we had subjects watch random movements of either the pendulum, the hand, or receive also vibrations without performing the task, which is motor imagery. And we report that there was an effect of the visual stimuli in the feedbacks. However, you can see it was the EEG activity is lower for the hand than the other two feedbacks, which is in the same order as our performance in the neurofeedback trials. However, most of the values are positive, meaning only watching the feedback without performing the task wasn't sufficient to induce a reward. So to discuss a bit about our results, we showed that the transparency of the visual feedback seemed to improve the BCI performance. So this replicates the finding from two previous studies. And one element that could explain this effect is the fact that when you observe someone of a virtual hand performing a movement, it's going to desynchronize your activity quite in the same way as when you imagine a movement. So this could explain partly why having a transparent feedback improved the performance for this experiment. However, for the visual tactile condition, the performance wasn't improved by the motor illusions. So this did not replicate the findings from studies that showed that adding vibrations improved the performance. So several factors could explain that result. It could have been that the vibrations were distracting and added a cognitive load to the participants, which made it harder to manage to do the task. It could also be that the motor illusion vibrations activated different networks, such as sensory motor integration networks that were located in different EEG spots than the C3 electrode that we used as a metric. For the agency effect, we compared different levels of transparency and showed that the more transparent the feedback, the stronger the sense of agency of the participants. So this is, to our knowledge, the first study to present such a result. However, the visual tactile conditions seem to decrease the sense of agency of the participants. So this did not replicate the findings from a previous study from Léa Piet and colleagues, which showed the complex results with an effect combined between the effect of time across sessions as well as agency on the visual tactile condition. One thing that could explain our results is the fact that the vibrations were a delayed feedback, and this is known to reduce the sense of agency of the participants. Finally, we report a correlation between the BCI performance and the sense of agency. So this also replicates a previous study that showed the correlation between the alpha desynchronization and the agency of the participants. And it would be interesting for us to try to run mediation analysis in order to find out if when you have a stronger sense of agency, this reinforces your performance, or is it when you have a better performance that it reinforces your sense of agency? So the key points of this presentation, we showed that feedback transparency seemed to improve for visual feedbacks, the sense of agency, as well as the BCI performance. Agency seemed to be correlated with the neurofeedback performance. And finally, we report that the visual stimuli contained in the feedback seem to impact the neurofeedback feature. So this should be something that should be reported in future studies. Thank you for your attention.
Thank you for your presentation. In similar, that's why it's got some codes. So thank you again for the presentation, very interesting. Do you have any questions from the audience? So feel free to raise your hand if you have any. In case I will ask all the questions because I have so many for you. Okay, I can start. Yes, I will have one question regarding the features you chose and the way you assess the BCI performance. You use a C3 for all the subjects, but did you try afterwards, to see if, for instance, for some subjects, you observe a desynchronization effect more in C5, for instance, or C1?
So we had 32 electrodes, so we did not have either the C5 or the C1. Maybe I can show you the actual set of electrodes. So we have preliminary results about the localization of the actual desynchronization. But we did not look yet at where exactly this desynchronization happened for most subjects, as we mostly analyzed the log data from the C3 metric we used to give the feedback. Yeah, I think that was our main hypothesis, that given that the feedback was based on the C3 electrode, it would mainly be specialized at this location, but that would be something interesting to look at to compare and to explain the different performances of the participants.
Any other questions from Jens? Sorry, we're trying to. So if not, I will be super chatty today. Okay, fine. Yes, learning actually is because I'm super interested in the way to perhaps extract some new physiological markers of the BCI performance. Perhaps also you could try to see whether you have differences in terms of functional connectivity, because you mentioned, actually it was a very interesting point, that depending on your feedback you received, you may involve different brain areas. So perhaps one thing to explore will consist in trying to see if you have different functional connectivity patterns depending on the feedback you provide.
So just to understand your question, that would mean I'm not really familiar with functional connectivity analysis, but I think that would consist in trying to see which electrodes fire together as a...
Yeah, how, for instance, in your case, you have in the sensor space, how two sensors can communicate between them. So you have actually plethora of metrics you can use to analyze and extract this information. But for instance, you can simply use the correlation, the most basic one, and you can use more sophisticated one just to see if actually you can see some difference in the way they interact.
I think, yeah, we maybe we had a discussion about it earlier. We were wondering whether, yeah, those kind of connectivity patterns could explain the differences of the results. We are trying to see if there is more of a lateralization effect as well. But since we had this metric on the C3 electrode that was kind of a fixed location for the desynchronization to happen. If we found out that the motor illusions made it more of a parietal desynchronization, that would be something to take into account for the future design of experiments.
Thank you very much. So I think it's time for our last speaker, but not least. So it is Andres Soler, who is a PhD student from the Norwegian University of Science and Technology. He's interested in brain source activity estimation. It's got a link between the two talks. And more specifically in low density EEG system. He used AI methods to reconstruct activity, classification, and to provide biomarkers identification and optimization. He will give a presentation entitled Channel Selection for Low Density EEG Source Reconstruction. Please, Andres.
Okay, thank you. Thank you all for being here. I would like to start showing my presentation. Okay, so I'm Andres Soler, PhD candidate for the Department of Cybernetics of Norwegian University of Science and Technology. I would like here to present the channel selection for low density EEG source reconstruction. First of all, I would like to start with a brief introduction. What is EEG source reconstruction, which is the estimation of the brain activity at the cerebral cortex that can be expressed in terms of the localization and the waveform or time courses of the source activity. For obtaining such images of the brain source estimation is required to have EEG data, the data recorded at the scalp, and also to have involved a model of the brain conductivity in order to obtain a better reconstruction or better estimation. There are some limitations for EEG source reconstructions with our low spatial resolution compared with other techniques of brain imaging. And also there is a problem in which is called the volume conduction problem, in which potentially all the electrodes can pick activity from all the different sources and they mix while they flow across the brain. So this makes harder the estimation. And across the years, it had been proven and evaluated that increase the number of electrodes or use high density EEG systems is recommended to do some reconstruction. Especially in the 1010 system, we can find up to 70 electrodes, or the 10.5 system up to 345 electrodes. However, there are multiple systems that are low density, they're based in low density, and for those systems is quite often that they can not do source reconstruction. So what we like to evaluate here is if it's possible to identify subsets of electrodes that can retain high density source reconstruction quality. And in that direction, we propose to do a channel selection approach based on ground truth activity and using the EEG activity. So we combine source reconstruction with channel selection. The channel selection was previously applied by Moctezuma and colleagues, and for features and classification accuracy. In this case, we approached source reconstruction, and what we did was to have the algorithm of optimization is non-sorted genetic algorithm. It creates a set of different combinations, and each of one combinations has multiple gens related to one of the channels. If the channel is 0, then the channel won't be used for source reconstruction, and if the channel is 1, the information of that channel will be used during source reconstruction. And we set 2 objectives, which were the number of channels, try to minimize the number of channels to use the lowest number of channels possible, while trying as well to minimize the localization error. So in that sense, we use 2 different frameworks to evaluate this proposal. One of them was using simulated activity. We simulated 150 trials of multiple source activity in multiple areas of the brain with temporal mixing. And also we include equal level of noise and signal. And we did this using a head model with 231, a very detailed model with of 161 scale electrodes, which were in positions, standard positions 10-10, and some of them in the 10-5 positions. We also evaluate this approach using the simultaneous intracerebral stimulation and high-density dataset localized ME, which was recorded by Mikula and colleagues. And it has 61 sessions of 7 participants with different intensities allocation, in which the activity, the location of the stimulation is known. So we use that as a ground truth for our localization minimization objective. And then for each participant, we had also available the anatomical information to create a forward model per subject. So in that sense, I would like to show some of the results of the optimization. First of all, here at the right, you can see what was the accuracy for 3 sources, the mean accuracy between the 3 sources across the 150 trials using 231 electrodes. And then on the left, you can see how is the optimization. This is the localization error by number of channels, in which the objective was to minimize the number of channels in this direction and to minimize the localization error in this direction. And then we found that we could identify different combination of channels that keep a low reconstruction error. In some cases, smaller than the reconstruction error with the 231 electrodes. And we detected that with 8 channels, we still could keep some mean error below the high density. And also in the around 60% of the trials, we obtain an equal or better accuracy than the full set of electrodes. And that number increased when we use 12 electrodes, in which more than 76% of the trials, we obtain equal or better accuracy. We did the same test, but instead of using the 251 positions, we restricted to the search to 128 positions, like a standard system for EEG recording. And then we found that it was still possible to find a combination of channels in the low density systems or numbers, in which we could keep still values below 5 millimeters of error and was lower than using the 128 channels. And in such cases, with 8 electrodes, we could see that 87 of the trials that we evaluated obtained equal or better accuracy than high density with 128 electrodes. Also, we did the same, but with the 10-10 system, with 60 electrodes of the 10-10 system. And then we start to notice that this curve obtained a higher localization error. And that is referring mostly to the position of the 10-10 system. Sometimes they are not the best for mapping the different locations. So then in here, anyway, we found that many of the trials, more than 91%, 85% and 67% with 8 and 12 channels, we obtain equal or better accuracy than high density EEG. So then we did the same, but instead of using this dataset, we use over the localized ME dataset, which has the simulation. And in this, we still keep similar, finding similar results, in which in here is shown the high density EEG results, the accuracy, the localization error. And in here, we can see that with a much low number of electrodes, we could still have better localization error than the full set of electrodes. and that for 70% of the trials with 8 channels, we obtain equal or better accuracy than the high density EEG. So then we would like to mention of conclusions in the sense that the proposed method to find optimize combination of electrodes can retain the localization accuracy of a high density system, and also that simplifying the number of electrodes by this optimal selection can be beneficial for multiple applications and systems based on channels in medical and non-medical fields, in which is required to extract the cortical activity of specific regions of the brain. So there are multiple devices in the market that lie in the category of low density EEG that can be used for monitor a particular source activity or a particular source brain function that can be monitored with a few channels. Also, there are multiple BCE systems that are based on brain activity and response of particular regions of the brain that can use this information. We believe that the use of source space in BCI system still is poorly exploited in some cases because there is the uncertainty of the reconstruction when using low density system. So most people don't dare to use source reconstruction if they don't have a high density system. And of course, there are some limitations in their work. One of them is the use of particular anatomical information, which sometimes is not available, especially in the non-medical applications. And also that I would like to highlight that the channels that we are obtaining after the optimization are channels that are related to that particular source activity. So different brain activities can be monitored by different combination of channels, and that is my final highlight for this. I would like just to mention the references, and I would like to thank my collaborators, and of course, thank to you for being here. I'm open to your questions.
Thank you very much, Andres. Do you have any question from the audience? He's quite shy today. It's fine. Okay, I will have one first question for you, Andres. It is really linked to your last comment, because I was wondering, did you study the spatial distribution of the selected electrodes? Because you mentioned that you, in the end, you select subset of electrodes, but did you investigate above which area they were located?
Yeah, so we, in both cases, for the simulation and for the real data set, the source activity was randomized in certain areas. I can show you like this, in which the simulation was in different regions of the brain. So each trial had different source activity. Okay. So what we wanted to evaluate is for different brain activity, we always can find such low numbers of electrodes that can keep the low reconstruction accuracy of the high density system.
And yes, regarding the different combinations you tried, did you obtain one combination per subject, or it was for the whole group of subjects?
No, we obtain one combination per each trial. Or in this case, in the case of the real dataset, one combination per each session, because the simulation was always in the same position. So we obtain like a small combination of channels for that particular subject and that particular activity.
Okay, and in the end, did you try to assess, say, the occurrence of a given combination over all the trials for one subject?
The combination, like evaluating if the combinations were the same for the subjects, you mean?
I'm sorry, it wasn't clear. I mean, for instance, if from one trial and another, you have a different combination of electrodes, and I mean, for a given subject, of course, did you try to see if one given combination was more often selected than another from one trial to the other?
Yes, but as the trials were different, then we always obtain different combinations.
Compare. Okay.
But if we look at the same trial, if we look at higher number of channels, we could see that a combination of lower number of channels were included. The same position were included in higher number of channels.
Okay. Any other question from the audience? If not, I can keep on asking questions. There is no problem for me. Actually, I learned a lot today, so I'm super happy of that. Yes, I was wondering, for instance, if you tried, because I saw that you compare different methods to perform source reconstruction. Did you try beamformer methods, which are more localized for a given brain area?
No, we just pick some of them, of the methods. Yeah, actually there are so many methods now,
yeah,
and we try to, yeah. So we just try to pick some of them, and in thus we pick this standardized low resolution, which is one of the most used, as well the weighted MBGNet. And we bought another from SPM software, which is the multiple sparse prior, to have also another view of the
because it's quite complementary to your approach, I think, because it really depends if you're interested in the whole scalp, whole cortex, or just a very more focused area. So perhaps depending on your scientific question, you could compare to one, for instance, the MBGNet methods, or to beamformer methods. So it can be of interest, I think.
Okay. Thank you for your suggestion.
Okay, so do you have any question? No? That's fine. So we can, I think we're on time so far. That's a good thing. And we can directly switch to the last part of this session dedicated to a general discussion. So as we previously see, the aim is to enable further discussion about the presentation, but also to provide some tips and feedback to the speakers. So since today people is very, very shy, I can try to start the discussion because beforehand we had a discussion between all of them. And I saw that two themes were super interesting to address today. The first one consists in the way to combine different modalities that we saw with Derek. In the particular case of BCI, we know that time is very crucial. So one question directly associated with the direct presentation is how to combine and analyze different time scales of neural dynamic simultaneously. Because we saw with specific modalities, but we also saw in the BCI or neurofeedback domain that it was possible to combine, for instance, EEG and fMRI, because we want to seize the opportunity to take advantage of their own complementarities. So the point here is to try to see if we can combine different modalities, and how is it possible to use such information to build online and real-time BCI systems. So in the meantime, just to give you time to think about this hard question, perhaps Derek, you can add a few words directly linked to your own research.
Yeah, so I think this is a really hard question. So far, like I haven't had any perfect answer for that, because we know that we can always downsample the one that has really high resolution, but this downsampling also force the limit the resolution that the original they can have. Yeah, tough question. Just want to hear everyone's feedback about this.
Help. No, because I think it's quite, I don't say usual, but it's a common question we have in the BCI domain, because many people are trying to combine different modalities, even between MEG and EEG, for instance. So I think it's quite relevant, and not quite, it is relevant for our domain to address such question. And I talked to this with Claire, and she found a nice review. I think it is from your group, Derek. I can directly share the link with you. And it was really interesting because in this review, just to make some advertise for your group, but that was very interesting because it actually addressed different modalities used to perform the BCI. And I think it's of interest because depending on your own modality, yes, Samantha? Okay, perhaps it's more general question. Okay, I will keep it in mind for later. It is very interesting to see how to combine them and to take advantage of them. From what I understood for the EEG and fMRI, for instance, one group from Rennes in France, they actually provided 2D feedback, and one dimension was directly linked to the fMRI and the other one to the EEG. So it's like a trick, but you don't actually combine directly for the same dimension the modality. I don't know if someone from the audience wants to share an opinion or to give some piece of advice. Okay, so if not, there is no problem. We can switch to perhaps first the question asked by Samantha. Regarding from your own perspective, what is the most limiting factor for wider adoption for BCI, sorry. So who wants to start?
I can go.
Everybody's super shy today. Please come on.
From my perspective, because for wider BCI has, or mostly the subject will be different. So when you develop a model analysis or recording modalities for one specific subject, it may not be performing pretty well for the other one. And also another important thing is that how to conversion between the hardware side and software side, because in the hardware we have advanced technology that keep improving the recording modalities, and also the software also has the path that moving forward. But how can we combine these like two advanced paths together? It will be a good question to all of us. Yeah.
Totally agree. I don't, Andres or Claude, you want to add something?
Yeah. I would like to add that to the comment to Derek, in which of course the subject variability is one difficulty that still I think is one of the challenges that is still work in process, how to improve the BCI performance using models of different persons. And another I think could be, of course, the access to the system itself. Like it's still very difficult for a person to get access to a system because the price, because the complexity of using it and the complexity of recording. So it is still a process. I think that could be one of the reasons.
I think I have quite the same idea about the issues we could have to try to get the BCIs out of the lab. The main, to my mind, the main problem is the quality of the signal, the signal to noise ratio. Because when you try to have an EEG system, for example, that is commercially available, you try to reduce the cost to make it wider with a wider range of customers possible, but so that would make your electrodes less specific and more difficult to pick up the specific activity you're trying to pick up on. And another aspect would be by the very notion of classifiers that are kind of a black box. This requires a lot of fine-tuning most of the times in the lab, and when you're trying to have users use it at home, and most of the times they don't have the knowledge to how you're calibrating, for example, your classifier and that kind of things. So I think that would be a main limitation, the lack of understanding and the lack of ways to bring understanding to how we calibrate and make the classifier work for the specific participants.
It's very fair points in my opinion, and actually I fully agree with all of your points, and it is really linked to another discussion we had the last day regarding how to find the trade-off between having a very standard, well-known and following the guidelines provided by the community, and also trying to adapt your system to the subject and more specifically to the patient. It's very hard because in the one way you want to have the same instructions for all of them, but then you know that sometimes even the way you express the instruction, you need to adapt the way you express the things to each participant. So I think it's quite a common question we all had. I mean, and even from your experience, sometimes it's very hard to find this trade-off because we saw with Andres regarding how many sensors you want to use to perform a well and a good social construction. As you mentioned before, you may be away from the traditional 10-10 montage. And with you, Claire, we saw that perhaps depending on the subject, you may be interested in using different sensors, as features to compute your BCI performance. And with Derek, we could imagine, for instance, that from one subject, one specific combination of modalities will work, but not for the another one. So I think perhaps, in my opinion, will be the most, hard and tough question to address. I don't know if someone from the audience wants to share his or her own experience on this point and to give perhaps tips for the trainees, because I think it's a very common question we all have, and it would be nice to have some feedback on this. Okay, we have one question from an anonymous person. So how will you use one sentence to introduce your research to the layman, like your grandparents or your relatives? Who wants to start? Come on, just one sentence.
I can start. Okay. I am developing a method to treat the potential neuropsychiatric disorders. Is it? I hope it is not too broad.
It's very short sentence, concise, perfect. Then Andres or Claire?
I can do it. I think the main, if I had to try to simplify the point, what we try to focus on is making using neurofeedback more intuitive for the user, so that a motor imagery task which is difficult becomes something we can do in a breeze.
Nicely done. A lot of pressure now on the shoulder.
Okay, I think to my grandmother, I will say that I'm trying to simplify the way we extract information from the brain. Yeah, I think it's that will be my sentence.
What a good way to finish this session. Thank you, Andres. So just as a conclusion of this whole session, first of all, to thank you all guys for this first session, because it was quite hard to manage because it's the first one. So thank you again for your presentation and your work, because it was very interesting and insightful. And also, I would like to warmly thank the members of the postdoc and students committee who helped me in the organization of the event, and with Sandrine, Vivek, and Iris. And finally, I would like to thank the board of the BSI Society that gave us the opportunity to propose you such a session. So feel free to contact us, by us, postdoc and students committee, to provide feedbacks on this event. And we are strongly interested in knowing your own opinion on this event. And for the trainees who are wanting to see, which kind of content you would like to see during the next event. So I think time is up and we're on time. So thank you all, and see you in May for the next edition of the Trainee Spotlight. Bye.
Thank you. Bye-bye.
Bye, thank you.
Thank you. Bye.